What if the next gold rush is underwater? Imagine a world where the riches lie not in mines, but beneath the ocean's mysterious depths. This isn't the plot of a science fiction movie, it's the future of deep sea mining. But how in the world are we going to mine the deep sea? Well, let's start with the basics. First off, the thing that you need to know is that deep underwater, around 4 kilometers down, there are these dark potato-shaped nodules. Now, what are nodules, you ask? Well, they've been sitting there for millions of years, slowly growing bigger. These strange small lumps might just hold the key to our electric future. We've known about these nodules since 1873, when HMS Challenger first brought up samples from the mysterious Midnight Zone, using kilometer-long ropes and a special collection device. Each of these nodules is packed with metals like manganese, cobalt, nickel, and copper, vital ingredients for modern battery production. It's estimated that an area slightly larger than Ireland could hold over 54 million tons of these metals, worth a staggering $20 billion. Until recently, these nodules were simply curious ocean floor features, since we could mine similar metals on land without the deep-sea challenges. But now, with global supply chain issues and the booming electric vehicle market, companies are racing to find new ways to mine these valuable resources. So, how do we actually get these nodules from the bottom of the ocean to the surface? Let's dive into the extraordinary process of deep-sea mining. Firstly, imagine descending into the deep sea. As you go down past 1,000 meters, it becomes completely dark and photosynthesis stops. The only light you might see is the faint glow of bioluminescent creatures. Without sunlight, food is very scarce, and animals depend on what's called marine snow, bits of organic material falling from shallower waters. Because of these extreme conditions, deep-sea creatures have evolved to become some of the most unique animals on Earth, like the translucent Dumbo octopus and the fearsome viperfish. Mining at these depths is no easy task. ROVs, remotely operated vehicles, and occasionally manned missions are used to explore and collect data. The Mariana Trench, the deepest part of our oceans, has only been visited by a handful of manned expeditions. Polymetallic nodules, our targets, form slowly over millennia. They grow on the seabed as materials like manganese and iron precipitate around a small rock or shell, similar to how rust forms on steel. These nodules are found in clusters across the Pacific and Indian Oceans, concentrated in areas with Pacific environmental conditions. Now, let's talk about extraction. When a mining operation is approved, specialized vehicles are deployed to scoop up these nodules from the seabed. These vehicles use pumps to lift the nodules, which are then transported to the surface for processing. Scientists can predict where these nodules appear based on environmental effects, and we found a higher concentration in the Pacific and Indian Oceans, mostly in international waters. To manage this, the UN set up the International Seabed Authority in 1994, based in Kingston, Jamaica, to oversee all mineral-related activities on the seabed. So far, they've granted permissions for 19 exploratory missions, primarily in the Clarion-Clipperton Zone and near Mexico. Why all the fuss? Well, these nodules are rich in metals crucial for modern technology: manganese, cobalt, nickel, and more. A single mining site could yield up to 1.5 millions of tons of wet nodules annually, potentially meeting rising global demands. But it's not without its controversy. Environmentalists raise concern about disrupting deep-sea ecosystems that remain largely untouched by humans. The delicate balance of these habitats could be irreversibly altered by mining activities. Mining operations pose direct threats to this fragile ecosystem. Heavy equipment could harm slower-moving deep-sea creatures, while sediment plumes may suffocate marine life. Noise and light pollution could disrupt feeding and reproduction patterns, affecting rare and long-lived species. Habitat destruction from mining could lead to species extinctions and hinder ecosystem recovery for centuries. Beyond ecological impacts, mining waste could harm open sea fisheries vital for food security, particularly in Pacific Island nations. Economic benefits from mining might not evenly benefit all nations, raising social and economic concerns. Moreover, disrupting deep-sea biodiversity could affect the ocean's ability to mitigate climate change by storing carbon dioxide. These concerns highlight the need for careful research and international cooperation before deep-sea mining proceeds. But imagine the potential of deep-sea mining. A typical electric car battery needs around 35 kilograms of nickel, 25 kilograms of manganese, and 14 kilograms of cobalt. If we mine the deep sea, we could get enough nickel for 400,000 car batteries, enough manganese for 18 million batteries, and enough cobalt for 100,000 cars every year. These resources are incredibly valuable, but we've never extracted solid minerals from the seafloor on a large scale before. This will require new technologies, many of which are inspired by the oil and gas industry and experts in deep-sea extraction. Firstly, companies need to find regions where the density of these polymetallic nodules make extraction worthwhile. Autonomous submarines use sound pulsars to map these regions. The current scanners can't pinpoint individual nodules. Physical samples are collected later to confirm the nodule's density. The challenging part is indeed the extraction. Several methods have been proposed to address various problems. Trials in the 1970s and 80s led to the most promising method, using a self-propelled rover. Connected to a ship by a sturdy riser and flexible pipe, technologies borrowed from oil and gas, it navigates the seabed remotely. Once the rover touches down, it moves around the seafloor, remotely operated from above. It acts like a potato harvester, but instead of soil, it uses a water jet to dislodge nodules and push them into the collector. The next step is transporting the material to the surface, which presents significant technological challenges. Raising material from such depths requires substantial energy, and pumping a solid material is much harder than liquid oil. Two main methods are proposed: pumping compressed air into the pipe to lift the material, which is energy inefficient at around 15%, or using submersible centrifugal pumps along the riser, the preferred method. Once on the surface, nodules are separated from leftover slurry and dried for transport. But dealing with this slurry, a mix of debris and water, is crucial. It can't simply be released at the surface due to environmental concerns. MIT researchers have studied dispersing it deeper into the ocean, below the layers where sunlight reaches, to minimize ecological impact. Their findings suggest that rapid dilution in ocean currents reduces sedimentation rates on the seafloor, crucial for protecting marine life. This method aims to avoid interference with filter feeders and other ocean organisms. But while there is no evidence of toxic elements in the sediment extraction from the deep sea, it's important not to compare it to the toxic tailing pools from the traditional ore mining. Unlike on land, where ore processing generates toxic waste, deep-sea mining primarily involves returning surface sediment to the sea. However, even if waste plumes have minimal impact, mining operations could wipe out species we haven't studied yet. Sea sponges anchor to the nodules, and deep-sea octopuses use them to lay and protect their eggs. These nodules take millions of years to form, so species that depend on them could lose their habitat, devastating an entire ecosystem we know very little about. One of the few studies on deep-sea mining's impact, dating back to the late 1980s off Peru's coast, found that seabed disturbances persisted for decades after nodule collection began. The affected areas showed lower biodiversity, with significant declines in filter feeders from other species. Other studies, like those in the CZZ, found significant loss of life, up to 20% compared to controlled areas. Now, we want to hear your thoughts. What do you think about this? Drop your thoughts in the comments section below. And if you enjoyed this video, don't forget to hit the like button and subscribe to our channel for more.